All right. Good morning, everybody. As Wasey said, my name is Carl Schuett from QED Secure Solutions.
Yeah, I'm Jesse Young from QED Secure Solutions as well. We do security research primarily with, we're a really small firm. When I say small, we're literally like 7 dudes that run around the country and do embedded device security research and assessments. We do a lot of medical devices. I just flew in from doing a medical device pen test. Planes, trains, but we actually try to do at least one project a year where we're just doing something because we're interested in it. And so we're going to talk to you today about some research we did on ACARS. I'll let Carl get into the more nitty-gritty details.
So real brief agenda here, what we're going to talk about today. Not going to spend any time on this one, but let's get into what exactly ACARS is in the first place. Stands for Aircraft Communication Addressing and Reporting System. It is a commercial carrier data link. It's how aircraft exchange data with the ground, and it was initially used both as a punch clock and as a way to kind of cut the chatter and eliminate voice communication so they could free up that traffic for air traffic control purposes. Covered by a number of ARINC standards, was first deployed in 1978. As I said, it started as a punch clock. It has since been expanded into a number of other roles. So when we say ACARS, ACARS is used as a blanket term, but really it is just the name for an application that is carried over some VHF transmission standards. So it's split up. You have the physical transmission standards, what we're talking about on the right-hand side here. ACARS is carried over the original standard, VHF Data Link Mode 0 or A, and now more commonly you see Link Mode 2. Those are the primary means of communications. They're not the only ones. SATCOM and high-frequency data link are used. Those are really good for areas where you don't have great VHF coverage, transoceanic flights, desert areas. They work really well there. And then you get into the applications themselves. So you've got the ACARS application, that was the original. Within that standard, the ACARS standard, you have a number of other applications that make use of the format. Air traffic surface, fans, controller pilot data link, and we're going to get into more details on those.
And so we actually came from this not with a whole lot of knowledge about like aircraft data links. We both have some experience prior to this doing aircraft stuff, but ACARS specifically we didn't. We wanted to look at where do we know things, and actually this is an excerpt from a document that actually tells this is how ACARS is implemented alongside with the OSI model. So if you are coming from this and you have kind of like a more traditional IT background, with ACARS, layer 1, the physical layer, that's essentially the transmission characteristics of this protocol. So it's phase shift keys. We'll get more into that a little bit later. It has a burst header at the beginning of the message that allows for transmitters and receivers to sync together. Layer 2, if you think about it in the TCP/IP model, where you have Ethernet there. You have similar message standards there with the data link layer. Uses a CSMA for collision avoidance and detection, basically like, hey, don't talk on the line unless it's open. Also has this thing called AVLC. AVLC stands for Aviation VHF Link Control. So again, more like control characteristics on layer 2. And then layer 3, the network layer, right? So you have AOA, which stands for ACARS over AVLC, so the ACARS application running on top of that AVLC frame. And then kind of a modified X.25 link standard, which again just helps with more data transmission characteristics. And so if you think about it, like there's a whole network for this application that aircraft and airports and air traffic controllers use, kind of like your internet service provider. There's a service provider network for ACARS as well. And if you think about it, you actually have to pay, like aircraft carriers have to pay money in order to transmit ACARS messages. So it's actually kind of a really expensive text messaging system for aircraft, but this is kind of representative of what you would see in a traditional, like the makeup of what a global ACARS network looks like. You have service provider networks, you have satellite ground stations, you have VHF, HF ground stations, you have airline traffic service units that do like ground control, things like that. You have some satellites up in space, and ultimately you have airplanes as well, which we collected a lot of airplane ACARS traffic during this research.
So to understand what ACARS does, we'll talk a little bit about how commercial aviation functions from an operational perspective. These are the phases of flight, and this applies to any commercial air traffic. So you have taxi. Taxi begins the moment the door closes. The taxi on the destination side ends the moment the door opens back up. So we talked a little bit about how this was a punch clock. Air crews are paid based on when those doors open and close. When they close, they start getting paid. When they open, they stop getting paid. So when they're loading you on the plane, they're doing that for free. So the messages are sent automatically via the radio based on sensor inputs connected to those doors, and that's these out, off, on, in messages that are highlighted. But as time has gone on and they've expanded the use of this, they've used it for a lot of other functions. Weather information, gate changes, just talking between pilots are all used commonly in ACARS messages.
Yeah, and so when you're up in the air and your aircraft is doing all this ACARS stuff, there's actually a lot of computers involved in that. So you'd imagine this is an RF protocol. You have to have a radio somewhere there. So off on the right-hand side, you see the VHF radio, or the unit itself is referred to as the VHF data radio because it actually does digital audio, at least the modern implementations do. And that all funnels into something called a communications management unit. And if you look at one of these things, it's actually just a box, right? It's not like a traditional computer that has a monitor and keyboard, but there are monitors and keyboards connected to it. And so you'll see other things attached to this CMU. You have interactive display unit, or IDU, which is kind of an old school version of like a monitor that tells pilots like, hey, this message is coming in from ground controller. But really nowadays you'll see more modern implementations with the thing on the bottom left, the multi-purpose control display unit. So you see it still looks kind of old school and busted, but they're actually they're used really often. That's still got the nice, green display, but now it's got some keypad items, some numbers you can punch in, some letters, as well as like a page up and page down. It gives the pilot an interface. Coupled with all of that, there's other things that need to use the communications management unit in order to communicate like their maintenance status. You see one item there, the digital flight data acquisition units, the DIFIDAL. That basically is your flight data recorder there. That emits messages over ACARS. You also actually have a cockpit printer as well that you can send a message to directly and it'll print out your text message on this printer. It's pretty cool. It's like a little old school. It sounds like a dot matrix printer. It's not actually a dot matrix printer, I don't think.
A thermal printer.
It's a thermal
Just
printer.
like for receipts.
Yeah. And lastly, this thing in the flight management system up in the top left, you can think of that as the brains of the aircraft. So all the phases of flight that Carl mentioned, the flight management system, the FMS, that actually controls all the phases of flight. And so all of this is happening while you're sitting, eating your peanuts at the end of the day. So it's pretty cool. This is just kind of an excerpt of what ACARS Mode 0, or what's referred to as plain old ACARS, looks like an actual waveform. So it's a VHF AM waveform. Those are the frequency ranges, but we actually normally turn it into the primary frequency, which is 131.55 megahertz. It does something called minimum shift keying, or what's also referred to as fast frequency shift keying. And if you look at the waveform on the bottom, you can see it's actually shifting back and forth between two frequencies. You see that shorter, kind of more tightly controlled waveform. That's the 2400 hertz. And then it oscillates between 2400 hertz and 1200 hertz in order to indicate a change in phase. And the change in phase is actually how you denote, like, hey, these are binary ones and zeros versus like a high or low point of the waveform. So that's something that Carl and I had to learn as well as we're kind of decoding all these messages that we were receiving.
So the transition to mode 2, you went from fast frequency shift keying to differential 8-phase shift keying. So this is an 8-segment constellation. It's groups of 3 bits, gray encoded. You've probably seen this elsewhere as well. But one of the advantages that you get from this is that you go from a 2400 bits per second data rate to an effective data rate of 31.5, and that's because of the group of 3 carried over a 10.5 kilohertz audio signal versus a 2400 hertz audio signal. A change in frequency as well. So the primary for mode 2 is carried over 136.975. If you wish to set up a receiver on your own, that's probably a good frequency to start at. But all of mode 2 channels reside only in 136 to 137, which is the upper end of the airband. So we did not have to write any decoders. This is a huge area for hobbyists, ham enthusiasts. There are plenty of open source decoders out there, and these are a few that we use that we'll get into a little bit more detail on. First, you have live ACARS. Live ACARS is not a decoder. It does not connect to a radio, but those decoders all use this because this takes the raw character data and converts it into meaningful information from the ACARS message. So provides a critical service to them and allows everybody to focus on the radio side and not so much on the ACARS side. ACARS deck, this was the original one that we started with, receives only plain old ACARS, can receive up to 8 channels simultaneously. That's more of a limitation of the software-defined radio you're using than the decoder itself. Accepts input from a number of radios. We used almost exclusively RTL SDR. Got some visual aids up here, but it does receive from others as well. Has some nice features, and these are going to be common across everything. Outputs data in JSON format, can output on a UDP port, so you can have, say, Plane Plotter or something else running as a listener in the background, picking up this information. Decodes a few formats, the formats that you see more in plain old ACARS, but not too much. VDL Mode 2 deck, this was our workhorse for our data collection. Receives Mode 2 only, but it receives, since that's most of the traffic, we got a lot of use out of this one. Written by the same person, so it has a lot of the same functionality. 8 channels, RTL, SDR input, output over UDP, output over JSON, the things that we need. This was kind of the Cadillac. Wish this was our workhorse, but we'll get into why later. Dump VDL, it has the same limitations, receives 8 channels, receives from the same radios. It just understands and decodes a lot more formats than the others do. It is also really good at piecing together multi-part messages, which is a thing in ACARS. We'll talk about this later. You're limited to 220 characters in the message. So if you want a message larger than 220 characters, you have to break it up into multiple parts and then reassemble it on the distant end. This one does that better than the other decoders. There's a few others that are out there as well. ACARS Deco, it's a quick and dirty command line, runs a little web server that you can use to observe your data. ACARS D, it's old, it hasn't seen any active development since 2006, but it uses your audio card, so you can use it in conjunction with something a bit like a Bearcat scanner. ACARS, all ACARS is over audio signals, so you can feed that data into your audio port and ACARS D will decode it. Multi-PSK is more of a ham radio tool, but it does understand and decode Mode 2 ACARS as well.
I was about to hold up the last piece, which is a Bearcat scanner. We have one up here. But again, we're looking at this kind of from a black box perspective. Obviously, there's lots of people that have built decoders. There's lots of documentation out there from the aviation industry. But we still wanted to know, what do these messages look like at the end of the day? So like traditional RF protocols, there is a preamble section that you kind of see on the top right-hand side there. That's traditional RF preamble type stuff, some syncing. I will call out a couple of fields. It might be a little bit difficult for some folks to see, but of note for us, there's an address, and so that address is actually the tail number of the aircraft. We have some examples later on that denote what that looks like. But basically that's the unique identifier for that message. There's also a message label. Message labels denote the type of ACARS message that you're going to receive. So there's tons of documentation out there that tell you all the different types of ACARS messages that you can receive. Some of them are weather reports, some of them are flight plan updates. A lot of them are actually free text messages, right? And so all of that text can actually be pumped into what we have highlighted on the bottom there, which is a message text field. It's limited to 220 characters. So you think a little bit more than Twitter, but I think a lot more expensive than Twitter. For this type of message that you have on the left, it's called a downlink message. So in ACARS, you have uplink messages and you have downlink messages. Uplink messages go up, so they actually go from the ground to the aircraft. Downlink messages go down from the aircraft to the ground, essentially. With downlink messages, you have to have some way to denote, hey, this is actually coming from an aircraft. So they actually take up the first 10 characters of the 220 to say like, hey, this is the message number just for some sequencing information in case I have to send multiple messages. And then the flight number itself, which I'm sure you're all aware of. If you've ever flown a plane, you have to know what your flight number is so you know which gate you're going to, so on and so forth. And that leaves 210 characters for like actual text.
So starting off with the old standard, the plain old ACARS or mode 0A, this is all you see. Ignore the metadata for now. The entire message is just what you see in the preamble and the message. And other than the transmitter sync information, this is it. Decoder metadata, all the decoders provide a little bit of information, what frequency you listen on, give yourself a unique identifier. But the interesting piece there is the preamble. So the label is important because that tells us what kind of message we're receiving and how to understand what's in the message text. The tail number for plain old ACARS was the only method they had for routing. So if it was an uplink message, only the aircraft with that tail number would listen to that message. Everybody else would just ignore it. On the ground side, the receiving end, either air traffic control, dispatch, the air operations center, would listen for their own tail numbers, and the data service provider will route it to them. But that's the only method they had available. And then you got the message text itself. This happens to be an ATIS message carrying a little bit of information about runway conditions and weather. So then you move up to the little bit more advanced. Now you're getting into mode 2, ACARS over AVLC. You get the addition of this AVLC frame. A little bit better for addressing and routing. You have unique identifiers for both the ground and the aircraft. Tail numbers can change over time. These do not. So routing becomes a lot easier. Also figuring out which one's uplink, downlink is a lot easier as well. But you still have the original ACARS standard at the base of this. You still have the same preamble. You still have the same message text. Then you get into this word soup. This is where you start to use the ACARS format to carry other information in the message text. So let's decode what exactly is in here. This, by the way, was captured with dump VDL. Dump VDL provides a lot more metadata. Probably the most interesting piece is signal level and noise level, so you can kind of determine the performance of your receiver. Then you get into the AVLC, or the actual ACARS message itself. Again, you still have that ACARS standard at the beginning. The standard really hasn't changed much since 1978. But if you'll notice, beyond the little bit of addressing information they put at the beginning of the message text, the rest of this is hex digits. That's because they're using what is primarily a character-oriented standard to transmit binary data. So something has to be able to convert the hex back into binary and turn it into something meaningful. And what that meaningful is this is controller pilot data link. It is a way to automate a lot of standard messages between air traffic control and the aircraft. In this case, an aircraft requested permission to depart. Air traffic control responded and said, yep, use standard instrument departures. Here's what you can expect. Here's your squawk code. Well, not finally. Well, the other one that we'll talk about a little bit here is ADSC, or automatic dependent surveillance. If you have even a passing interest in this stuff, I'm sure you know about ADSB capture. This is an antenna for picking up ADSB. ADSC is very similar. It just doesn't carry anywhere nearly as much information. Operates within the ACARS format. It doesn't run at the 1090 megahertz that ADSB does. But it is still just a way to transmit information to air traffic control about where you're at. CE stands for contract. It is technically a contract that the aircraft makes with air traffic control.
And so we've kind of gone into the academics of ACARS. We threw a lot of information at you to try and help paint the picture of like, this is a radio standard at the end of the day, which a lot of enthusiasts collect, but it's largely used by the aviation industry. A lot of the aviation industry is black box, right? Because they like to keep to themselves. But software-defined radio is like commodity these days. So we thought, hey, we could do that. We could build a software-defined radio platform that uses all of these decoders, and let's see what we can collect. So it's Raspberry Pi based. I have one up here. Like, I'm sure most people have seen a Raspberry Pi at this point in their careers, or if you haven't, then like this is one. We'd be happy to talk to you about it afterwards. But essentially, we installed these software decoders onto a Raspberry Pi and hooked it up to a really low-cost software-defined radio. And Carl and I travel all over the place, and so it's nice to just like have this little nifty project that we're doing as we're traveling around. We had two versions of an antenna. We essentially have this really small, like the standard antenna that comes with the RTL SDR, And then in the next slide here, oh no, sorry, that's my fault. In an upcoming slide, we have like this massive base station antenna that Carl actually put in his backyard here in Omaha. So you'll see this other block diagram. We have ELK ingest. Our talk title is learning to speak ACARS using ELK. We'll get into that infrastructure as well. But here's just a little bit about the big base station antenna that Carl has in his backyard. So obviously this is kind of what's referred to as a J-hook antenna. And Carl pieced this together with some copper pipe, some PVC for stabilization, and he's a lot more nifty than I am. He actually has some masonry skills and built a wooden stand there to stand it up in his backyard. I don't think his wife was happy about it being up all the time, so it's...
Neither were the neighbors.
Yeah, neither were the neighbors. But this is essentially $50 worth of materials that you can acquire either at the hardware store or some of the cable we had to get on Amazon, but super accessible.
Sharp-eyed radio viewers will probably note a mistake in the antenna that we can get to at the end if we got time for questions. So the radio, we already talked a little bit about this. If you have even a passing interest in software-defined radio, you probably have 2 or 3 of these at home. RTL SDR, based on a mass-produced TV tuner chipset, but you can get them for about $30. You can still get these for about $30. They have a nice frequency range. They work perfectly for what we're doing. They also work really good for collecting ADS-B. They have a 2 to 3 megahertz frequency range, which can affect what you're trying to pick up depending on how far apart frequencies are spread out. But again, the price makes it a really attractive option for collection.
Yeah, and so we'll get into why we have this ELK Stack piece involved. We're collecting all these messages, and ACARS is actually really noisy. There's tons of messages just flying around with the ACARS protocol at all times, especially if you live near an airport or if you travel a lot. You're going to just be there's going to be ACARS all around you. So tons of data. We're doing tons of traveling, and so we thought it'd be nice to put this in something other than an Excel spreadsheet at the end of the day. And we figured we do what everyone else in the security industry is doing, and we'll just throw it in an ELK Stack. So for those of you who aren't familiar with ELK Stack, it's one of those big data solutions. Elasticsearch gives us search and index capability and some analytics. Logstash that helped us do the message ingestion and kind of the parsing. And then Kibana ultimately gives us those fancy web HTML5 dashboards because I'm really bad at coding anything UI. And then the file beats piece. I think most people use some type of beats thing with their ELK stacks these days. That just helped us with the log ingestion as we were getting new ACARS messages from our software-defined radios. That would take care of pumping it into the ELK stack. So this is our infrastructure. Of course, on the left-hand side, we have multiple sensors. So Carl had one, I have one. We hand some out to our friends. Ultimately, that data goes to a relay, which we have just hanging out on DigitalOcean's small cloud provider. It's an Ubuntu box that we pay $5 a month for. And as we were learning this standard and how to kind of parse and ingest these different messages, because there's tons of different message types, and they all kind of look a little bit different, we'd actually stage all this stuff on a relay box, this DigitalOcean box, and that would allow us to write the parsers as we were analyzing the data, message by message. And those parsers would actually go in our Logstash instance. Logstash does a lot of the heavy lifting with message parsing, custom filtering, a little bit of pre-processing before ultimately we throw it into the Elasticsearch instance, which gives us all of our fancy keyword search terms that we're interested in doing. This is kind of just a more fine-tuned, I guess, block diagram of what we have. So sensor input on the left, our Raspberry Pi device, that goes into our relay box that's on DigitalOcean just for staging while we're kind of waiting for things to be parsed properly and while we tweak those settings. Ultimately, once we're comfortable with the message filter, we get it, FileBeats picks them up after the relay pushes those logs, those messages, which are really just JSON blobs at the end of the day. All those decoders actually output JSON, which is kind of why we thought ELK Stack would be nice to parse all this data. Logstash does filtering and parsing, and ultimately pumps it over to, we chose to use the Elastic Cloud service on AWS. I know there's other ways you can deploy ELK stacks, but I'm really lazy, so I just wanted to click a button and have an ELK stack in, I don't know, like 5 minutes. For those of you who aren't familiar with having to write custom parsers or filter for a Logstash, this is indicative of kind of what we had to do. So this is just one ACARS message type, and Carl will get into all the different types of ACARS messages there are, but this is just for one message type we had to do. Obviously, some of the messages have positions in them, latitudes and longitudes, and we know that ELK actually has a really nifty way to take latitudes and longitudes and plot points on a map automatically for you. So we thought, oh, that would be really cool. So we took this piece. We had to ultimately expand that to this piece here, which is essentially a big filter for one type of ACARS message, specifically an H1 message. So sometimes there are latitudes and longitudes in them, sometimes there aren't. So just want to illustrate to you here, we had to do a lot of custom work because for the security industry, as I'm sure you're all aware, there's lots of like pre-built log parsers and pre-built event filters that'll just like do security analytics for you on an ELK stack. But there's not that for ACARS, so we had to do a lot of customization and writing here. And this is just one of those instances.
So our collection effort was over about a 3-month period. We collected a total of 852,000 messages from 4,900 unique aircraft, covering 190 different labels. And since those labels define the message types, that gives you an indication of just how many different message types there are. Just a quick, here's what our frequency spread is. On the left-hand side, that's where the primary frequency is. So you can see that's where most of the traffic appears, but they also use the other end of that 136 to 137 range as well. Count by label. You'll notice on the very, my right-hand side, those are actually acknowledgements. If you can see the very bottom of that, those are acknowledgements. We'll talk about that later. Probably would normally filter those out. But what is interesting is the second piece, which is the H1 message type. That was the second most common. We would have expected a lot of cockpit printer messages, free text messages, but no, H1 is interesting because H1 is intended to be routed to another system on the aircraft, usually without pilot interaction, or at least nothing more than pilot acknowledgement that it has been received. This is what is used to get information into the flight management computer, into the DFIDAL, into the CMU. Just a spread by tail number, since I collected here, a lot of regional flights passing overhead. So most of these are actually regional aircraft. So kind of some guides for interpreting what you're looking at. Labels, 10 through 4 something, and the label number can be alphanumeric and include punctuation. So there's more than 30 or 40 message types in there. Those are user-defined, so we'll use this specific example later on. Label 32 is used by SkyWest for position reports. It can be used by every other airline for something completely different. So you have to match both the label number and the airline to try to determine what's in there. If you see a flight number that's GS, or actually a lot of zeros, chances are that's a charter flight or a business jet flight. If you see XA in a flight number, that could indicate a military flight, but a better indication is the tail number. The tail number for military aircraft tend to be all digits. If you see X in a flight number for a common carrier, that is probably a charter operated by the common carrier. And then finally, if you want to do this as a hobby, just don't collect in the UK. Their telecommunication laws say if you are not the intended recipient for that message, you cannot listen to it. And so if you follow things like live ATC, you typically won't see listeners set up in England. So one of the things we looked at was position information. And while this is certainly not the only thing that's in ACARS messages, it does kind of tell us how well the antenna is performing, what kind of coverage we're getting. We got about a 150-mile radius all the way down south of Kansas City, north of Sioux Falls and Sioux City. But you'll probably also notice some trends, some lines passing through there. Those flights, they follow the same exact routes every day, and so you kind of see those patterns emerge, and you see the most common vectors that aircraft are using. Chicago O'Hare, despite being a crappy airport, has a great Hilton on the property that is 10 floors high. If you are lucky enough to be on one of those top floors and you have a window facing the airport side, Great place to set up a mobile antenna, hook up your Raspberry Pi, and let it listen for a day or two. I think this was only about over a 48-hour period or 24-hour period. And again, you can kind of see those trends of the paths heading into the airport. Chances are they're vectors heading in. Do you mind holding on to your question? Okay, thanks. We're kind of running behind, that's why I'm asking. So what can you do with all this information? Well, if you're going to fly pretty soon or you have a favorite airplane, maybe you want to follow just that airplane. So here's an example here. We're looking at N890DN. It's a Delta aircraft. Frankly, no industry probably has more OSINT sources than aviation. Everybody loves to follow aviation. This is a picture of that plane because FlightAware has pictures of most tail numbers that are currently operating and some that haven't. If you ever see a tail number in a Hollywood movie, there is a website that will tell you the history of that airplane or helicopter for that movie and how it is used in Hollywood. So let's look at some of the traffic and what N890 is talking about. These are H1 messages. Again, these are messages intended for what is most likely the flight management system. In fact, I think the very first two characters in the text, M1, that indicates a flight management system. If you'll focus on the July 9th message there, one of the things that's interesting about that is that you'll see what are waypoints. So if you've got even a passing interest in aviation, you might know what that is. They're just points at particular latitudes and longitudes they can use to ease navigation. You'll see here they got Jackson, Woody, and Heather. And so you can take that information out of this message. Again, go to another OSINT tool. SkyVector is used for flight path planning. You cannot use it to make official flight plans, but you can use it as a tool to help you. If you're not a paid customer, you can still throw in the waypoints and still get vectors. So what we saw in that message is dispatch sending a flight plan to N890DN, automatically telling it, here's the route that you're going to follow, here are your vectors heading into what is, in this case, SeaTac. All of this done with nothing more than just maybe an acknowledgement from the pilot or the air crew. So a little bit of information, by the way, sidestep here real quick for airports. Runways are set along the predominant winds in the area. So if you're looking at Epley Airfield here, you can see that most winds blow mostly southeast or northwest. And that's why Chicago looks like this, because Chicago is a tornado of garbage.
Carl really likes Chicago.
Hate Chicago. The other things that you can do with this tool is you can kind of aggregate data to figure out what it's saying. This is a notional example, but just kind of what we're talking about here. This is that label 32 that we mentioned earlier, used by position reports for SkyWest. But you don't know that. SkyWest isn't going to tell you what their data formats look like. So we can look at this information. If you had one sample to look at, you can tell pretty easily, okay, there's obviously latitudes, longitudes, there's a time code in here. You can make some guesses about the other fields, but you don't know for sure. So if you look at 6 and 7, when you take a whole bunch of these messages together, it is a 5-digit field. It never gets larger than 40,000. It's probably an altitude. The one right next to it, field 7, 3 characters, never goes over 360. It's the aircraft's heading. And then you can use that kind of like to guess, okay, what exactly is being said in this message.
Yeah, and so in addition to reverse engineering custom messages or air carrier defined messages, we're kind of just interested in using like, okay, we have this giant ELK stack. It's costing me a bunch of money per month. Like, let's search some stuff in it. And so we started looking for things. These are messages, again, H1 messages. So from the flight management computer, from the central fault display. And the central fault display you can think of as the aircraft's like really fancy dash where you can get things like your oil temperature, and but a lot more than that than what's in your car, right? Like you can get oil pressure, you can get the pounds per hour of fuel that are being burned by an aircraft. So really interesting stuff that just comes out of the aircraft automatically and is just being emitted over RF. Some other interesting message from the central fault display, like which FADEC is controlled. So the FADEC is the full authority digital engine control. So that tells you, just collecting, like, hey, this particular FADEC is in control, because most aircraft have at least two of everything for safety purposes, right?
So taking off in an aircraft is not like just leaving in your car in a driveway, obviously. Again, if you're following your favorite aircraft to see what you can expect on takeoff, This is a way to tell, okay, exactly how fast am I going to be going when the wheels get off the ground. So just like you can say, okay, well, what's wrong with my aircraft, like Jesse was talking about, what type of performance problems might I expect, I can also look at this information as well. So you might recognize some of these fields. V-speeds are probably the most obvious. Flap positions as they're taking off. What does the pilot have to do as they are taking off to maximize fuel efficiency and make sure they meet their minimum weight requirements? V1. V1 is the speed at which, once you pass that, if anything is wrong, the aircraft has to take off and troubleshoot whatever is going wrong in the air. Anything below that, they can still brake. VR, that's the rotate speed. That's the moment where the pilot can pull back on the stick and actually take off.
Yeah, so just some other interesting tidbits that we pulled. We have all this data. We have an ELK stack. We can search keywords in it. So we were like, what happens when we type in medical emergency? Are we going to see anything interesting there? And the first hits we actually got were cargo information. So the example on the left, we happened to get a hit on the word emergency. It's an emergency telephone number. But we thought it was kind of interesting because this is actually a message destined to the little printer that prints out in the cockpit. And it's a manifest. It's a cargo manifest. So it tells the pilot, like, hey, we loaded some fruit and produce on some fruits and veggies on your aircraft, also some cherries specifically, which I don't know why that didn't fit in with the fruit and veggies to begin with, but I don't know, not my aircraft. This is actually a message destined for, I think, an Australian aircraft. Also on the right-hand side, notification to the pilot, hey, we're loading some special medical reagents onto your aircraft, so just be aware of that. In addition to that, we actually did get some medical information transmitted over ACARS. So some of the other hits were like, hey, we're having a medical situation. This is a flight from Las Vegas to Chicago. This passenger is seated in 11A or B, and you can see where we've blacked out. It's actually somebody's name, right? Like somebody's name. They have pancreatitis and asthma. They're having difficulty breathing. So wow, that's actually information that we just got listening over the air. And then the message on the right is like, hey, I wanted to make sure you got my message about the medical emergency. So this is all happening, around us all the time. And we just thought it was interesting that we could collect it.
And on the medical side, by the way, when it comes to HIPAA exposure, you may have even heard of this before. We are definitely not the first person to note this. Probably just interested that it is still happening. It's a paper by Matt Smith from 2016 talking specifically about HIPAA exposure because ACARS is unencrypted. So less dramatic than medical emergencies, you also have lots of weather information. It's critical that flight crews understand the weather conditions when they are departing and arriving at an airport. It determines how fast they need to go, determines what kind of crosswinds they can expect. So ATIS is primarily this information. If you are listening to voice communications, there's always a channel that's broadcasting ATIS information constantly. And if you ever listen in on control information as well, if you ever hear a pilot say something like, I have information Zulu or Delta, they're talking about, I have the most recent ATIS information. And this is an example of that just in text form. So if you look at the, again, my right, you can see in there where it says like a BKN 021. I should have mentioned this earlier. These are short messages, lots and lots of abbreviations, lots and lots of shorthand. So broken clouds at 2,100 feet, broken clouds at 5,500 feet. That A3004 there, that's the altitude. They have to set the altitude based on pressure in the local area so that it's correct when they come in for landing. And then the one on the other side is just a lengthier version of that, flying into Miami, lots of construction going on, so the pilots need to know what runways can I expect, what taxiways do I need to avoid.
Yeah, and just some more fun stuff. You can also send what are called free text messages over ACARS. So these are messages that the pilot or the ground can physically type into their terminal and send over ACARS. So some of the interesting hits we got were like this example on the left-hand side is, hey, that's old dude's leaving. I think after 10 minutes we can go again. I'm sure you've all seen lots of cool videos of people getting kicked off aircraft over the last 2 years for non-compliance. We saw a lot of non-compliance messages go over ACARS as well. You can see we blacked out like that's a name. So, hey, if you got kicked off an aircraft, we probably collected your name somewhere. And then last but not least, on the right-hand side, it's probably the most important message that we would see, like the coffee maker isn't working. 74 hits out of all of our message on the term coffee. This is another piece that we thought, like, obviously we're security researchers at the end of the day, and we had a lot of fun collecting this information, kind of learning how to parse. This is a hobby project for us, but there are some interesting security concerns beyond that of like, hey, this is unencrypted. This is a message that's called a MEAM data transfer. A MEAM data transfer is a media independent aviation message. This is specifically from an Airbus aircraft, but you'll see once you decode it and you look at the data itself, the message content, it's markup language, right? So it's not XML, but it's XML-like. So we're curious if, you know, the aviation industry is pretty black box, as I mentioned. How much effort has there been placed into fuzzing this type of protocol, right? Are there serialization, deserialization vulnerabilities here? So we thought this was interesting as well.
So that's kind of a large summary of what we collected through our ELK stack. But I want to swing back around to dump VDL specifically, just because the way it operates actually impacted our ELK stack. Dump VDL, I mentioned earlier, it's the Cadillac of collectors. It understands a lot more protocols than everybody else does. But that comes with one really big downside that Jesse's going to talk about. One nice thing that it does for us is, again, if you go back to that support for multi-part messages, it's a lot easier or a lot more friendly to look at that information and figure out what's going on. Things like CPDLC are definitely larger than 220 characters. This is an example of an entire flight plan. It's a lot easier to look at it through dump VDL than it is to have to go back and try to reassemble this yourself by guessing what you're getting from a single aircraft. You know, this thing includes all your waypoints, what you can expect for fuel burn rates, all the way down to aircrew signatures. This would go to the printer, they'd print it out, they'd sign it off. That's their paperwork. They're always talking about the reason for their delays. When you get into the decoding CPDLC, ATS, they're binary formats encoded in hex characters. We can actually read what's going on in there. This is something that, while VDL Mode 2 DEC is good, it does not capture a lot of this information. It's nice to see this parsed out. Also, not that we intend to operationalize this anytime soon, but if you did plan on operationalizing this, you can, because it has built-in health monitoring. It sends out its data via StatsD. You can set up a Grafana instance and actually keep track of how well your collector's running, or if it needs to be restarted. If I've got this running at home and then I got to go on the road, I can monitor it and I can restart it if I need to. It's kind of a nice feature, unique, but getting into the drawback.
Yeah, so obviously I've been talking mostly about the ELK stuff. Like the ELK stack was kind of my thing. But dump VDL2, which is, you know, Carl described as kind of the Cadillac of converters, it creates like tons of nested JSON to which, if any of you are running like your own ELK stack, parsing the nested JSON within nested JSON within nested JSON is really expensive on the compute side. And you know, since we're doing this on our own, I'm paying for the ELK stack out of my pocket. And at first I was like, yeah, it's just a button, I'll click it, and I'll get an ELK stack. It's actually super expensive. So I think there are AWS folks, maybe they can give me some of my money back. But essentially, we were like, okay, we're not using this all the time. We just want to, you know, query it every once in a while. So I actually bumped the performance down. And once we were parsing all of these JSON fields, our ELK stack actually tipped over, like it just fell, right? And so I'm sure there are people somewhere in this conference that are way better at like service reliability and things like that. But dump VDL2 definitely taxed our collection infrastructure.
So what were our lessons learned? Message filtering. We opened our aperture as wide as we possibly could when we first started this up because we wanted to make sure our receivers were working. That includes collecting all those acknowledgments. They don't add anything to the aircraft conversation. They're not interesting to us. Filtering that out would have saved a lot of workload on the ELK stack side. So definitely something we would implement if we were doing this again. Multi-part messages. Those tools we were talking about, they're open source tools. We've actually done a few minor improvements to those and then pushed them to the original developers. There's no reason we can't do that for something like VDL Mode 2 as well. That's something that we would definitely look into.
Yeah, and then the final bullet there, capture infrastructure costs. You know, I kind of joke about AWS giving me some of my money back. It's my fault at the end of the day. You know, I didn't architect it the way that it probably could be best utilized, but it's expensive. I think at our peak performance, I was paying like $400 a month for some of the like really heavy duty searching and analysis we were doing. So that's why we're doing it from slides and like not live right now. But in conclusion, kind of our takeaways from all this, these big data tools, we realized we can use these to analyze, structured data that there aren't like common use cases for. Maybe they weren't originally intended or envisioned by the developers to be aggregated in that way. So we thought that was really interesting. Also, we probably realized, apart from the aircraft carriers themselves, individuals probably aren't aggregating ACARS data like this at scale. And so we thought, there's probably risk to data exposure when you do that collection at scale.
Last two, there's really no confidentiality mechanism. There is secure versions of ACARS. They're not used. We might have seen a couple of instances of it. It's just not very common. Why? This has been used since 1978, realistically without a problem. It's already really expensive. There's not much of a reason to change anything if it isn't currently a perceived problem. But then our final takeaway, step away from the security side a little bit. It is just a cool hobby that can be used to learn something about a wide range of domains. Learn a little bit about SDR and RF, learn a little bit about aviation, learn a little bit about big data tools if you want to set up your own AWS instance and spend $400 a month. Yeah, with that, that's it, guys. That's our talk. I know we're running into the next one here. Do you guys mind if we answer his question, because he's been waiting patiently this whole time, but if you've got 10 minutes? Okay, go ahead.
I noticed a bit of granularity in your screenshot of plane positions over Chicago. Like there was a grid pattern.
It definitely looks like a grid, like they're rounding off the lat long positions, yes. And it depends on the type of message. Some messages have like 1 or 2 digits of precision in the lat long, and we just look for anything that looks like position data, so we think that's where that rounding error is coming in.
So you mentioned cars not going away anytime soon or anything like that, and I'm just thinking, with it being an older standard, so like, I don't know, I work at Union Pacific, and they're working on anywhere to mainframes, because it's like everyone that knows mainframe is going away, and so they won't be able to maintain it anymore. Do you think anything like that could be a situation with cars, or is it just radio signals are good to go?
So the aviation industry is notorious for its slow rate of change, right? The nice thing about this is that the infrastructure can change and be kind of agnostic to the standard. I'm sure that they're using better and better radio equipment, especially on the ground side, because you don't have to worry about affecting type certification. If you've heard recently about the issues with 5G being broadcast too close to airports, that shouldn't be a problem. It's only a problem because of the glacial pace that aviation proceeds at, because if they allowed filters in the data radios and in their navigation instruments that keep the side channel interference from 5G out, which, by the way, are extremely common, they could have 5G on the airport with the aircraft. They just don't, because every time you make a change to any system on an aircraft that affects its type certification, it's years to turn around and make that change. MCAS with the 737 MAX, one of the reasons why MCAS was an issue is because if Boeing had made all of the changes to the 737 MAX that they should have, they would have exceeded this magic 15% threshold of change to the aircraft, and then they would have had to re-accomplish type certification, which is like, I don't know, it's ridiculous. It's like a decade-long process. So MCAS was a workaround to keep under that magic threshold.
Yeah, just one more tidbit too with ACARS. Like, it's not going away at the end of the day. It's an older standard, but it's heavily dependent on. So you see more and more of these applications get layered on top. We showed you the OSI implementation, right? So even the security side, secure ACARS, encrypted ACARS, yes, that exists. People develop it, but there's no incentive actually for folks to use it, because ACARS, it's a pay per message protocol. So the moment you add more messages just for the sake of encryption, you're asking to pay more money, and no one wants to do that.
You're paying by character, literally. So.
Question right here.
Question. Are the ACARS messages also backed up on the aircraft in the black box that's really orange, for analysis after the fact, and in case of any need to investigate things by NTSB, and or if they wanted to have a capture of the messages so they can see what messages were we trying to send versus what messages were actually received on the downwind side.
Does the diffidal record ACARS messages?
So we can't say this definitively, but most telemetry is captured by, you got the cockpit voice data recorder, which just captures like a rolling 30 minutes or whatever was going on in the cockpit. And then the digital flight data acquisition unit is supposed to capture all telemetry information. That means anything from the air data computer, the CMU, everything, and then a subset of that is passed along to the flight data recorder, which captures all the telemetry. So that can be entirely dependent on the airline and what they choose to put on their flight data recorder. I would say at the very least, it's probably archived on the ground, because whether it's coming from the aircraft or the ground, somebody can pick it up and you can archive all that information.
Yeah, ground maintenance is a whole nother box of can of worms that we don't talk about here.
All right, any other questions?
Any worries about uplink data injection to change flight?
No, absolutely not. 100%, we would never try such a thing.
No.
But if we were to try such a thing, and we wouldn't, definitely would not try such a thing ever, I will tell you that building a transmitter and building the waveforms for the data, unfortunately, is a lot easier than trying to build a quality receiver, because as the transmitter, I just have to worry about the properties of the waveform and that they are well formed. The receiver is the guy that's got to worry about the differential and the noise reduction and the filtering and removing side channels. So we certainly have never seen any indication of traffic injection. We know there's been attempts to do so, or I'm sorry, not attempts to, there's been research into that. The research descriptions have always been, we're doing this in a Faraday cage. It's isolated. Yeah, we're not broadcasting this in the open. Obviously, broadcasting on a licensed band is definitely illegal, and if you do it poorly, or if you get yourself caught, you're going to be in a world of hurt. Yeah, yes, exactly. All right, we're at 5 minutes, and I know we got to switch over. If anybody wants to catch us out of here, I want to make sure there's time to do all the cutover for the next speaker. But thank you very much for everybody for coming out. Hope you enjoyed this.